Okay, terrific. So this is video 2 of 2, hopefully only 2, of D.1 Stellar Quantities, I think? Stellar Processes? I forget. D.1, whatever that is. Stars. So we have epsilon Indy, it's 4600 Kelvin. What's the peak wavelength? Let's use is it Wien's law, I think? Yeah, I'll get that equation rolling. So this is a D2 question, but it's still not hard. We see lambda max T is a constant. And the constant is baked into the formula on the data booklet.
What broke well?
And we get a lambda max of 6.3 times 10 to the negative 7 meters, or 630 nanometers. Alright, so we need a black body curve shape, and the peak's going to be at 630 nanometers. So the highest point, I think it just says sketch the curve. Yeah, it doesn't specify any y-axis values, but the peak's going to be right there. And then the black body curve I can show you. And the black body curve is kind of like a normal distribution, but it's skewed left towards the lower wavelengths. Let's say towards longer wavelengths. Higher, lower frequencies, longer wavelengths. Wait, no, it's skewed towards the shorter wavelengths and higher frequencies. It skews left. So there we go. So we don't actually know the radius of the sun, and it's not a constant in the data booklet. We do know that luminosity is Stefan Boltzmann, a 2 to the 4th, and the area of a sphere is 4 pi r squared. We could go after relative luminosity, because it seems that that's what they're giving us. They're asking for relative luminosity. They're giving us the relative radius, so we can do all of these things relative, epsilon Indy relative to the sun. And so we get relative luminosity is Stefan Boltzmann times 4 pi. And actually, constants, just as constants don't affect proportional expressions, they don't really affect relative expressions either. But let's actually get into why that's true. So here's the relative luminosity of epsilon Indy versus that of the sun. And so we can see that all of the constants cancel out. Ding, ding, ding. And so when you work that out, the radius of the sun squared drops out. And so we get 0.73 squared times the relative temperatures, both raised to the 4th. And when you work all of that out, we get that the relative, you get like L over L naught, which is what they're looking for. Or like that the luminosity of epsilon Indy is 0.21 of the luminosity of the sun, which is what the mark scheme says. They have 3 sig figs. Why do they have 3 sig figs when the radius is given to 2 sig figs? Whatever, it's 0.21. And that is a D1 question. Alright, that was 10C, now let's go for 10D. Okay, so 10D says that epsilon Indy's main sequence show that the mass is 0.64 the mass of the sun. So that's one of these relative mass situations with the 3/5 going on. Again, this is another D2 question, but we're seeing a lot of that. And remembering that this relationship for main sequence is a relative relationship, and that's really what they're looking for anyway. They said show that the mass of epsilon Indy is 0.64 the mass of the sun. Well, we just figured out the relative luminosity, and that is 0.21. And we need to get rid of the 3.5 power, so we raise both sides to the 1 over 3.5. And we get a relative mass of 0.64, so yes, indeed, the mass of epsilon Indy is 0.64 the mass of the sun. I feel like that's a lot for 1 mark. I feel like there should be 2 marks. Also, of course, is error carried forward from the previous question, which doesn't actually say that in the mark scheme, but there has to be. 10E. How can chemical composition of a star be determined? You fly to the star with a giant tablespoon, and you scoop up a tablespoon of star, and then you sip on it. And you're like, no, not how it's done. You observe the stellar spectrum of the star. That's stellar spectrum of a star. That's redundant. You observe the spectrum. Use a spectroscope. And you look for which frequencies are absorbed or missing in the absorption spectrum of that star. And then you compare that absorption spectrum to the known reference elements to the absorption spectra of the known reference elements here on Earth. Let's see what the mark scheme says. Obtain line spectrum of star compared to laboratory spectra of elements. Nailed it. All right, 10F. Stages in the evolution from the point when it leaves the main sequence star until its final stable state is going to be the same as the sun. Oh, actually, do we know that for a fact? Let's see, it's 0.64 the mass of the sun. Right, so it's not, what is it, 1.3? I forget what the limit is. But yeah, it's under 1.3 or thereabouts the mass of the sun, so it's going to follow the same path as the sun. So we go from the main sequence to a red giant phase, which is larger, cooler, and more luminous. And then we eventually get to the white dwarf phase. And a white dwarf is much smaller, and it's hotter, and it's less luminous. But that's the leftover core. And in between, it's kind of like, well, if that's the core, then what happened to the rest of the star? Like, you go from a red giant to the core being the white dwarf, but like, what about the rest of it? Where does it go? It kind of drifts away and surrounds the star, going back to a nebular form. And so that would be the planetary nebula in between. It's a gas surrounds core, I guess. I didn't know that planetary nebula was actually in the curriculum, but that is a thing. I think I mentioned that in class, and that is a stage of what happens. It describes what happens to the rest of the star. Then the planetary nebula drifts away, and what's left is the core, which is the white dwarf. Constellation and open cluster. Again, with the constellation and open cluster, they're obsessed with this question. I'm not even going to write the answer. Just look at this mark scheme. These are the details. When you're a constellation, the stars look like they're close together on the celestial sphere. They are probably not. Most likely not actually close together. In an open cluster, they actually are close together and so are gravitationally bound. Also, in that cluster, all those stars were made at roughly the same time. That's why they're close together. So they're similar in age. What else does it say? It says clusters originate from the same gas cloud. Yes, because they were made at the same time, so they came from the same place. Constellation stars are not, because they're not actually close together. So thankfully they give 5 different ways, and they only want 2 marks. They only want 2 different ways. I would say probably the biggest difference, if you ask me, is that constellation stars are not actually close together, whereas open cluster stars are. So that's this guy, the third point. And I would say probably that even though open cluster stars are close to each other, that doesn't necessarily mean that they're the same age. Or stars being close together doesn't necessarily mean they're the same age, but then why would they be close together like that? And the feature of open clusters and what are also called globular clusters, star clusters, are that they were made at roughly the same time, so they're of the same age and also roughly the same temperature. So I would say if you're going to pick 2 points in this list, those are the most important, I would say. And we're also on number 11. Number 10 is over. 10F. Lots of parts to number 10. So now we're on 11A. All right, but now we're on 11B. And so we have a parallax question. Mintaka. Mintaka is one of the stars in Orion's belt. Anyway, so we know the parallax angle. Let's figure out how far away Mintaka is. That's not hard. So the distance to a star in parsecs is 1 over its parallax angle in arcseconds, which would be 1 over 3.64 times 10 to the negative 3, which is, watch it be 275. Well, will you look at that? It's 275. And that actually is to the correct number of significant figures. What a shock. let's swing over to here. I wonder, why do I grid the pages? I should just make them in a line. It doesn't make a difference. So I don't have to go back and forth. Whatever, okay. So 11C. Maximum distance that astronomers can measure using stellar parallax. Mark scheme says difficulty of measuring very small angles. We can elaborate on that. So yeah, there becomes a point when that parallax angle for the star falls into the uncertainty of our best instruments. And so if your measurement is so small that it falls within the uncertainty, then you can't really say, like if your uncertainty is, you know, plus or minus 100%, like then you basically have no precision at all, do you? So then, yeah, that becomes problematic. All right, 11D. Great Nebula is in Orion. Using Jeans criterion, what is the condition for the nebula to become a star? Shenanigans, I tell you. The Jeans criterion is 11.4. I asked for questions on 11.1. Ugh, whatever. I'm going to answer it anyway because all these questions are fair game when it comes to astrophysics. But let's talk about the Jeans criterion. It has nothing to do with denim. Dum-dum. And so basically, I mean, I think I've said in class in kind of a hand-wavy way that you have a nebular cloud. That nebular cloud collapses under its own gravity, gets denser and denser and denser, and eventually becomes a star. Well, it's like, yeah, well, how big does the cloud have to be? Like, does any cloud of gas become a star? Like, absolutely not. And so what's the lower limit? And that lower limit of how much mass you need to actually become a star, that is the Jeans criterion. So first, the star needs to be dense. It needs to have a certain mass per unit volume, but mostly the mass. And so within that volume and the amount of mass, the mass of your cloud has to be greater than what's called the Jeans mass limit. That is not a constant. That depends on a number of things. You don't need to know that equation or what those things depend on. Just know that the mass of the cloud needs to be large enough, bigger than the Jeans mass limit. There's one other thing that's important, and that's the potential energy of the molecules versus the kinetic energy of the molecules. So the gravitational potential energy in the molecules has to be greater than their average kinetic energy. We know average kinetic energy, basically what I'm talking about there, is temperature. So in other words, in plain English, it can't be too hot. Because if the cloud's too hot and then you go in to compress it, the kinetic energy, the molecules, they bounce off of each other, and you're not going to be able to really compress and coalesce into a protostar. And we see that here in the Mark scheme. The mass of the gas cloud is greater than the Jeans mass. Gravitational potential energy is greater than the average kinetic energy of the particles. And so the cloud collapses to make a protostar. Great. 12A. That was it for 11? That's it for 11. All right, now we're on 12. Peak wavelength of the radiation emitted by Epsilon Indi. Congratulations, you did not actually tell me what I need to know. Also, we already did the Epsilon Indi. This is a repeat. Black body did that. Relative luminosity did that. 12D, blah blah. 12E. 12E is different. Alright, so we did, let's see, 12A through D, but we did not do 12E, where it says Sun will spend about 9 billion years in the main sequence. How long will Epsilon Indi spend on the main sequence? Alright, so yeah, this is another D4 question. Thank you very much when I asked for D1. But this is D4, and I'm looking at, let's see, and even though everyone's like, oh, there are no formulas for D4 in the data booklet, I found a formula. It's in the notes. It's not actually on the data booklet. So be advised. But anyway, we're talking about Epsilon Indi, and it says that the relative period of a star relative to the sun is the relative mass to the negative 2/5. And that actually comes from relationships off of the what do they call that thing? HR diagram. It's related to luminosity being proportional to mass to the 3/5. Since it's not in the data booklet, I should show you how it's derived. Alright, let's have a little sidebar here. So we know that luminosity is proportional to the relative luminosity is proportional to 3/5 times the mass. That is given in the data booklet. And we know that luminosity is measured in watts. And so luminosity is in watts, so it's power. So luminosity is energy over time. That's the energy that a star is putting out as a function of time. So the energy that a star pretty much turns mass into energy by fusion. So any energy that is lost is mc squared. And so then the time, therefore, the period of the entire star would be its luminosity. If you convert the entire mass of the star, it'd be the mass of the star times c squared over its luminosity. And so if the relative luminosity is proportional to the relative mass, and we have that the time and the period is proportional to, so then period is proportional to m over the mass of the mass over m to the 3.5, then basically what we get is that the relative lifetime of a star, period, is not equal to, proportional to mass to the negative 2.5. So the relative period is proportional to the relative mass to the negative 2.5. That's kind of where that is coming from. Now, we can actually reach back. We already found the relative mass between epsilon Indi and the sun. That's when we already solved this problem the first time, and we got that the relative mass is 0.64. So let's actually bring that back over here and save us some work. And so the period of our star is 0.64 to the negative 2.5 times the period of our sun, which the period of the sun was given to us somewhere 9 billion years. It says right there in the question. And we wind up with 2.75, or 2.7465, whatever. So 2.7 billion, it's 2.746, so 27 billion years. What does the answer say? 27 billion years. Now, they did it another way using relative masses and luminosities, but I mean, I use the derivation from the notes, but the derivation from the notes makes sense. So either way, there you go. That's a D4 question. Did they say people got that one? Yeah, they just said NA. I don't know. I feel like that one's kind of funky, but there you have it. I think it's also, I guess it's not a lot for 2 marks if you know what you're supposed to be doing. But anyway, so that's E. And then F says, describe what happened to epsilon Indi. We already did that. One thing it says in the mark scheme, though, don't accept supernova, red supergiant, neutron star, black hole. That's because of the mass of epsilon Indi relative to the sun. It would not achieve those stages. So those are not acceptable. All right, and then I think that's it for 12, and we're up to 13. So let's cross off everything else from 12 because we already did it. So no, because they were all repeats, and also no. But 12E was worthwhile. And so let's move on to number 13. Distinguish between solar system and a galaxy. I think we already saw that question too. And I mean, the mark scheme kind of describes galaxies larger than a solar system. Duh. Galaxy has more than one solar system. I mean, duh. Every star has a solar system. And a galaxy is more luminous. Yes, certainly. There's only one star in a stellar system. Galaxies have many stars. So, like I said, any other valid statement, I think that's pretty good. So I'm just going to be like, let's see. So there you have it. It's only 1 point anyway, 1 mark. Distinguish between a planet and a comet. I don't know if we saw this one yet. Planets and comets, there you go. I would say the biggest thing is the close and far orbits. If I had to remember something, planets are close in, comets are far out. They're the farthest things out there. There. Comets generally have, not generally, they all do. Well, define larger. I guess, it's the radii are larger for comets. Oh yeah, comets have a tail, planets don't. That's true. You have gravitational compression pulling inward, but thermonuclear fusion pressure pushes outwards, those pressures equilibrate, and you have yourself a sphere. You have yourself hydrostatic equilibrium. There, made it look more like a star. Oh, this is number 14 as well. 13 didn't have much to say. So now we're on 14. Remembering that in L is proportional to m to the 3.5, those are relative. So it's asking for the relative luminosity, and it gives us the relative mass, 1.3 times the mass of the sun. So really we just say 1.3 to the 3/5 is 2.5. So the luminosity relative to the sun's luminosity of star P is 2.5 luminosity of the sun. Luminosity equation, I'm going to look up Stefan Boltzmann. Remember that area is 4 pi r squared. And then we get the luminosity is 4.10 times 10 to the 29 watts divided by the luminosity of the sun, and we get a relative luminosity of 1060. I did notice one typo in the mark scheme. That's 4.1 times 10 to the positive 29, which they have correct here. And then 14D with the parallax, the angle may be too small to measure without having huge error, or may actually be too small to measure whatsoever. In that case, we can use Cepheid variables as a standard candle, or even type 1a supernovas. 14E wants the main sequence on that HR diagram. Got to make sure you get the center where a star would be, where a sun would be. And it's kind of like a wavy S situation, not like that. Maybe something that looks like that. Here's the mark scheme. 14F says plot the star from B. Relative luminosity is 2.5. Temperature is 3600. Well, actually, Gacrox is not necessarily 14B. We don't know the temperature from 14B. It does say main sequence star, so it's going to be in the main sequence. So it's 2.5. This is a logarithmic scale, so it's going to be close to 1. Somewhere like there. And then they want Gacrox for 14G. Gacrox is like 1,000 times the luminosity of the sun. So Gacrox looking at 1,000 the luminosity of the sun. Gacrox would be about there. Hold on, no, it doesn't actually say that Gacrox is main sequence, but we do have a temperature for it, 3600 Kelvin. There, it's outside the main sequence. Okay, 14H. I don't know what they mean by star P, but I guess like of any star, if it's in the main sequence to its final stable phase, discuss with reference to the change in mass, the evolution of that star. So I feel like the mark scheme, we just read the mark scheme. It'll just tell you. So different things you can say. Main sequence to red giant, and then becomes a planetary nebula with mass reduction. And goes from planetary nebula to a white dwarf. Or you could go main sequence to red supergiant, and then you have a supernova, or a neutron star, or a black hole. I would say most stars are going to take this normal. This is the most common route. Even though the other two options, the other one option could happen. If this is this alternative too, if there's more mass, it could become supernova, or black hole, or neutron star. 15. Oh, finally, we're moving into the next question. What's main sequence? Mark scheme says stars fusing hydrogen into helium. My understanding is that all stars do that. It's just a question of what happens later. I will tell you, though, that my understanding of the main sequence is that the luminosity is proportional to the relative luminosity is proportional to the relative mass raised to the 3/5. Okay, so 15b uses the main sequence luminosity mass relationship. So 40 solar masses would be that the relative mass is 40. And we have the luminosity relative to the luminosity of the sun. So yeah, relative luminosity is 4 times 10 to the 5, relative mass is 40. So 4 times 10 to the 5 equals 40 raised to the 3.5. To two significant figures it is, so yes. So luminosity is Stefan Boltzmann area T to the 4th. But this is all relative to the sun, so we have to treat this formula from a relative perspective as well. So the constants cancel out. We know the relative luminosity is 4 times 10 to the 5th. We know that the radius of theta 1 Orionis is 13 times that of the sun. Don't forget r is squared. And we know the surface temperature of the sun. So we're solving for T, the surface temperature of theta 1 Orionis. So when you work the numbers out, you get 42,000 Kelvin. So one significant figure, the actual relative luminosity is one significant figure. It's really 40,000 Kelvin, but whatever. So yeah, 15D uses the distance is related to the relative brightness, but all of the numbers were given in relative values to the sun. So that's why I replaced all of the D, L, and B with relative values. And if I'm looking at a relative perspective, the constants cancel when you divide, they divide out. So the reason why I'm looking for the relative distance, because the distance in AU is the distance to the sun. So it's kind of like a relative distance kind of thing. So we have the relative luminosity is 4 times 10 to the 5th. The relative brightness was given as 4 times 10 to the negative 11. Divide that up in square root, and I get that the relative distance is 1 times 10 to the 8 astronomical units, or the distance to the sun, which is 1.8 astronomical units, which matches. 15E, I think the mark scheme speaks for itself. 1, radiation pressure pushes against the gravitation pressure, and then that radiation pressure is due to the fusion in the core. That's the second point. I feel like if you just said radiation pressure, that would have been sufficient, but I guess they do want you to mention the fusion. Yeah, it says pressure and force is inappropriately mixed. That's annoying, but I guess they're right, because pressure is force per unit area, and then only 1 point for unexplained hydrostatic equilibrium. I would agree with that because you have to show what hydrostatic equilibrium is. But I guess they require that you say why there's radiation pressure. I think they should modify the question. But anyway, there you go. So one thing to understand about theta 1 Orionis is that it has 40 solar masses. That is well more than the sun. It's beyond the Chandrasekhar limit. It's beyond the Oppenheimer-Volkoff limit or whatever. And so looking at the Mar scheme, it says sun will become a red giant, whereas theta 1 Orionis will become a red supergiant, getting really big because it's already much brighter and bigger than the sun. The sun will explode as a planetary nebula, become a planetary nebula, but theta 1 Orionis will explode as a supernova because its mass is so much bigger. And then the sun will end up as a white dwarf at the end, but theta 1 Orionis will either be a neutron star or a black hole after its supernova. And the reason why is because of its mass. 40 solar masses is big. So, for that reason. Two more questions, 16 and 17. 16A, the elements. In the core, there's helium. In the outer layer, there is hydrogen. And the hydrogen fuses into helium, which goes into the core. Because the helium is more massive, so it'll collapse into the core. And for a regular star, there really is not much else going on. Typical main sequence star. Okay, let's see 16B, talking about the main sequence. All right, this one's a bit of a doozy. So density is mass over volume, and we get the relative mass from the relative luminosity, and except we have to take luminosity proportional to m to the 3/5. That means that relative mass is proportional to the relative luminosity to 1 over the to raised to 1 over 3/5. Luminosities are given from the HR diagram. I can see that x is 10 to the 4 and y is 10 to the negative 3. And then, so if when I work those numbers, I get that the relative mass of x to y is 100. Then volume is 4/3 pi r cubed. That's a math formula from the data booklet. Relative volume, I take the constants out and just get radius of x cubed over a radius of y cubed. The radii I get from the HR diagram, x is 10r, y is 0.1r. And when I do 10 to the third over 0.1 to the third, I get a million, 1 times 10 to the 6. So density being mass over volume, I get mass of x over volume of x over mass of y over volume of y, which is a complex fraction. You can resolve that out to mass of x over mass of y times volume of y over volume of x. The relative masses is 100. The relative volumes is a million, but it's y over x, so it's 1 over a million. So I have 100 divided by a million, and I get 1 times 10 to the negative 4. And that agrees with the mark scheme, 10 to the negative 4. So yeah, I was starting to think this topic was easy. That is not an easy question. Let's move on. So 16C says draw a line to indicate evolutionary path of star X, and it says draw a line to the right. It will get hotter over time as it approaches the white dwarf stage that will eventually become a neutron star, so its temperature will increase. That's why it says line to the right of X, very roughly horizontal, so that it increases, they will progress higher in temperature for 16C. And then 16D says, after the supernova stage, why does the neutron star not collapse into a black hole? Because there's not enough gravity. It says gravitation is balanced, or there's not enough gravity by the pressure because of neutron degeneracy. The neutrons are squished close together, and they're not going to be able to get any close together without even more gravitational pull, which will then crush everything into a black hole. But it's not hitting black hole because of the neutron degeneracy, pushing back. 16E, we have the radius of the neutron star and its surface temperature. What is its luminosity? And I'm beginning to realize that sometimes the mark scheme just does it well. It's using L. Luminosity is Stefan Boltzmann area t to the 4th, and of course surface area is 4 pi r squared. So we have our Stefan Boltzmann constant right there. We have the radius, the area right there. We have the 4th power of temperature right there, and so we wind up with 3 times 10 to the 26 watts for our answer, second mark. All right, so D2 for 16F. The maximum wavelength is proportional to the temperature by that constant. And then the temperature is actually right over here. It says radius is 20 kilometers and surface temperature is 1,000,000 Kelvin. So using those numbers, we wind up with a lambda max of we get 2.9 times 10 to the negative 9 meters, which is a gamma ray. Oops, I meant an X-ray. I hate going back and forth. X-ray. I thought that was a little long for a gamma ray. I don't know why I said gamma ray. I thought that everything was like gamma rays. These are X-rays. They emit X-rays. Pretty cool. Okay, a binary star system. Mark scheme, 2 stars orbiting around a common center of gravity. I don't know. Do not accept 2 stars orbiting each other. Really? That's interesting. I guess you have to say common center of mass or gravity. I thought orbiting each other would imply that, but I guess not. So don't forget about a common center of mass or gravity, right? All right, then 17b, it says calculate the relative apparent brightness, and then we have the luminosity of the sun. What is the radius of Alpha Centauri A? I see that we have the information for Alpha Centauri A and B. We have their luminosities and we have their surface temperatures. All right, so you have apparent brightness when the 4 pi divides out. Since we're dealing with the binary, the distance also divides out because they both have about the same distance. So the relative apparent brightness ratio is going to be the relative luminosity, and we have those numbers. And so the brightness ratio is 3. They said 3.0. Yeah, they have one significant figure on the luminosity for alpha B, so no, it's just 3. But that is the first part. The second part, it says luminosity of the sun, calculate the radius of Alpha Centauri A. Let's just use the answer down here. We're getting radius because here's where the radius comes from. Luminosity is Stefan Boltzmann, area t to the 4th, area is 4 pi r squared. Solve for r. It's radical L over Stefan Boltzmann, 4 pi t to the 4th. Now this 1.5 times 3.8 times 10 to the 26 is because Alpha Centauri A, its luminosity is 1.5 the luminosity of the sun, and the luminosity of the sun is given as 3.8 times 10 to the 26 watts. That's where that is coming from. Then we have 4 pi. We have the Stefan Boltzmann constant, the 5.67 times 10 to the negative 8. And we have the surface temperature to the 4th in the denominator. And so when we get the radius, we get 8.4 times 10 to the 8 meters. That's where that's coming from. Naturally, we should be writing in the boxes, but this is a lot of D1, so I'm just trying to get to the end. It's tantalizingly close, so let's wrap this up. All right, so luminosity is Stefan Boltzmann, area 2 to the 4th. Area is 4 pi r squared. The two temperatures are very similar. It's like they're in the 5,000 Kelvin range, so we don't need to worry about the comparison on temperature. And we're talking about radius. So radius is going to be square root. I want to make sure I do this right. Let's see, we have R is radical L over Stefan Boltzmann 4 pi. Those are constants. So pretty much the radius of the star, these two stars, since their temperatures, temps similar. So then radius is proportional to the square root of the luminosity. A has a bigger luminosity than B. Luminosity of B is less than the luminosity of A, right? Right. And so therefore the radius of B is going to be less than the radius of A. Where can I put that? Therefore, R of B is less than R of A. All right. And so that was 17C. 17D, alpha A is in equilibrium at constant radius. How is the equilibrium maintained? We can just look to the mark scheme. That's pretty basic. Radiation pressure from nuclear fusion pushes outwards, gravitational pressure pushes inwards, and then the pressure is balanced. I think this is nonsense because somewhere else in the mark scheme they said do not accept force and you must say pressure. This one says that force is acceptable. So is it one or the other? That's kind of messed up. Say pressure, it really is force per unit area that's doing the pushing. You're better off saying pressure than force. That's 3 marks, huh? I guess. Yeah, I guess you say like radiation pushes one way, gravity pushes the other, but they have to reach equilibrium. That's the point of that. So that's your 3 marks. 1, 2, 3. All right, 17E. Is this the last one? This is the last one. Cool. All right, draw the present position of alpha A and its expected evolutionary path. So alpha A based on luminosity and temperature. So the luminosity of A, it's 1.5 L star, L sun, and it's 5,800 Kelvin. 1.5 and 5,800. 1.5, which is roughly 1, and 5,800, which is pretty much by the sun. So alpha A is pretty much near where the sun is. And then it will become hotter and more luminous as it gets older, but then it will burn out to like a white dwarf that is cooler and less luminous. So it kind of like goes like this way in terms of its evolutionary path. I guess red giant gets like a little cooler but gets brighter, and then eventually comes down to white dwarf later on. And that's what it says there. Okay, and that's that. Yeah, this 10 through 17 was longer than I expected. But that's all of them. All right, let me come back to where this was and stop.